Hi. So I only had lunchtime to prepare this, but I'll keep it short. I'm working together with a friend of mine on building a compact microcomputer from TTL logic. So on the left you see Marcel, who started this all in December of 2016, and I joined him. And we were inspired by computers from the 70s and 80s, like the Apple I computer that you may recognize on the top left. And we wanted to recreate something like that. And we were also inspired by stuff like the PyDP-8. Maybe some of you have built it yourself. There was a Dutch guy who built a do-it-yourself kit to recreate the original PDP-8 computer using a Raspberry Pi. But although that was an interesting kit where you had to solder some LEDs onto a board, we would like to take it one step further and let you solder by a kit with parts and solder it to form a complete microcomputer built out of these kind of chips that were already available in the 70s and 80s. So we did cheat a little bit. So for instance, the power is supplied by a USB cable, which didn't exist in the 70s. But we tried to stay as close as we could to the 1970s and 80s components. So this is all through the whole easy soldering stuff that you can build yourself. And the nice thing is that these things are still available in the market today. So there's a lot of stuff to talk about, but let's just point out two little things during the design, which has taken already, it's not finished yet, but it has taken since December last year. There were a lot of design decisions to be made, and most of the design decisions were made because of the way the hardware works. So everything was assembled on a breadboard, and we went from there to see what can we incorporate, how can we improve the hardware. So one of the interesting things, I think, is that in computers you have you used to have the Harvard architecture, where you have a separate memory for instructions and a separate memory for the data. And this was abandoned in the early 40s by the people making the ENIAC computer. And there was one guy, Mr. von Neumann, he wrote a paper about it, so it's now bears his name, the von Neumann architecture, where you have one memory that stores both the instructions and the data. So this is what we're used to today. Our kit uses the Harvard architecture, so it has advantages and disadvantages. It makes for a simpler design. It makes it a lot faster. It's easier. But of course, it also has disadvantages. For example, if you want to put stuff into the data memory, you need to write a lot of code that copies all kinds of bytes into data memory. So that's a bit of a hassle. And in fact, when you look at the whole design of the computer, we have made some design decisions where we made a decision in favor of easy hardware. So we have quite easy hardware that's simple and fast. And the problems that will give you need to be solved in software. But software these days is much more easy than it was in the Apple I days. Another thing that's interesting, and my friend Marcel wrote about it on Hackaday just this week, is that we use pipelining. Each instruction in our computer is 1 byte, and each byte has 1 byte of data. So you have 2 bytes. 1 byte is the instruction and 1 byte is the data. Even if the instruction does not need data, there's always a byte for instruction and a byte for data. And we don't have microcode. So if you look at processors like the 6502 that you will find in a Commodore, if you send it an hardware instruction inside of the CPU, there will be several steps, maybe 7 steps that need to be taken to perform that action, to perform that opcode. In our computer, everything is done in 1 cycle. So that's really, really fast, but it limits the amount of opcodes that we have. But again, that's something that we can solve in software. What's also interesting is that we have one clock, and the clock is delayed. So we have actually 2 clocks, one clock and 1 delayed clock. In 1 clock cycle, we can work on the opcode and the data that's been clocked in, and then already the next instruction can be fetched. So from the memory, we take an instruction and data. It's being pushed into registers, and while that is executing already, we take the next instruction from memory. And this makes for a really sleek design. You know that everything is 1 clock cycle, but again, the software becomes a little bit more difficult. And to show you how, let's go over that side for a moment. So, for example, when you have a branch instruction, something really weird happens. Because if you do the branch, then during the execution of that instruction, the next instruction is already fetched from memory and put into the system. So in the top, there's a bit of program that says load 0 in the accumulator, and a little bit further along the lines, it says branch to address 0. But if you do the branch, so that's taken from memory, put into the register, and while the branch is executing, we are already fetching the next instruction, which is in this case the no operation. And that is also executed in the next step. So this is really completely weird. You do the branch, but the instruction next to the branch is also executed. But we can use this. We can say, we can change this and say we branch to position 1 instead of position 2, and instead of using a knob, we duplicate the instruction on address 0, which then gets executed. So it's really ugly, but it's really fast. And this can be optimized in software. So we started out by making all kinds of stuff on breadboards and using oscilloscopes. And we plan on doing a full talk about this at the CCC3 conference, or the CCC conference. Might you be interested in knowing more about this project? The URL below you can use to subscribe to our announce mailing list. So I guess that's all the time I have. Thanks.